All right. Good morning and welcome to my talk about embedded security nightmares. Now, before I'm actually going to go to the main part of the talk, just a very quick introduction of me. Hi, I'm Sven. I love to make devices do stuff they're not supposed to be doing in general, mainly embedded devices, but also computers and just about everything. I used to work on the Wii a few years back and helped create the Homebrew channel, which a few of you might have used. What I did there was mainly writing the exploits to actually get it onto the system. But I'm probably most famous for my PlayStation 3 work, where I was eventually sued by Sony because I broke their whole security system. Yeah, so that's right. So, but what I'm going to talk about today is embedded systems in general. And if there's anyone in here who loves to spend their whole day staring at IDA, reversing binaries, finding really, really obscure bugs, you'll probably be bored. Because I just want to do this as a very general talk. If you have a little bit of background with reverse engineering maybe, and you have some kind of embedded device at your home, maybe a mobile phone, some kind of media player, and you want to break into it, I'm just going to present a few bugs that everyone does over and over again. Because vulnerabilities are kind of like ideas. You're probably not the first one who thought of it. And there's a very good chance that the vendor of your device made one of those mistakes, which I'm going to present. And hopefully afterwards, you'll be able to use this on your favorite toy at home and maybe port Linux to it or make it do something it should not be doing in the first place. But what exactly are embedded devices anyway? So I've already talked about consoles like the Wii, the Xbox, the PlayStation 3, and so on. Those are definitely embedded devices. There's also your phones, your smartphone, yeah, also any kind of phones, and of course media players, and pretty much everything that runs some kind of code that is updatable. For example, there's also smart TVs these days. They even run Linux. And there's a good chance that in your room there's at least 5 different embedded devices. You may not even be aware of some of them. I think these days also the Tesla car is also running some kind of Linux variant or something like that. There's really lots and lots of things. And in general, there's also 2 categories. Sometimes the vendor is a little bit lazy, so they just take Linux, port it to their device, add a little bit of security, and then ship it and think that it's insanely secure and no one's ever going to break into it. And then there's those vendors who spend a little bit more on security and who actually think a little bit more about the whole system's design, and they completely write their own operating system. The difference here is that the second kind usually thinks about security from the very first, before even the very first line of code is written. So those devices are generally harder to break into because the whole system was designed with the idea, we're going to give this to customers. We don't want customers to do whatever they want to do, so we want to lock them down. And if the whole system is designed with that in mind, it's usually harder to break into. Whereas Linux, it's not really made to lock you out of your own computer, your own device. So they usually slap on a kernel module that's supposed to enforce code signing or something like that. And those are generally very, very easy to break. Another question is, why do vendors even add security? Because probably everyone in here, if you would be building some kind of product, you'd probably make it open source, ship it with a Linux kernel or whatever, and just allow the end user to customize their devices. But those big evil corporations, they usually want to add something to digital rights management. They don't want you to steal things. They want to collect license fees from third-party producers. That's, for example, very big in the gaming consoles, because they usually sell their hardware at loss, and they only make money by selling the games. And because they don't want to make the games themselves, they force others to pay them so that they are allowed to make games for their system. So there's lots and lots and lots of reasons why people invent, or why people add security. And why should you care about breaking it? Well, I mean, the first answer is pretty obvious. It's fun, or why shouldn't you care about it? And, well, you can also do it for science. Just because you can is the first part. Now, the second thing is, especially for Linux-based devices, there's usually a low barrier of entry. So if you've ever wanted to become a famous hacker or something and just just break into something, whatever, start with a small embedded device. Make sure that it's running Linux, and you'll very likely be successful very, very, very early, because general developers don't have a clue about security. They just read some Wikipedia page maybe, or some standard book, and then think that they can build the perfect security system. And, well, you'll see what's going to happen in the next few slides, because there's usually lots of logic bugs and really, really stupid screw-ups. And usually you don't even need to write shellcode to break any system of that kind. Because, well, yeah, because they just suck, mainly. And then there's also end-of-life products. So you may have some kind, for example, I have a media player sitting at home that was end-of-life like half a year ago or something. And it's just running Linux with XBMC on top of it, but a really old and outdated version. And there's lots of bugs everywhere, and I would like to fix them myself. So the only solution to that is to break into the device. Here's your mandatory Neo slide for any hacking presentation. Right, so as I mentioned, if it's running Linux, it's going to be very easy, because chances are they used a serial port during bring up. So a serial port is just a really, really simple two-wire protocol. You have a receive and a transmit line. And after they have done all their debugging, installed all their packages, and they want to ship it to the end user now, they just forget that there's still this UART thing there. And most of them are even nice enough to label it for you on the PCB. So the first thing you do, get some screwdrivers, take apart your device, and just look around. If you see something like TX or TXD or RX or RXD, it's very likely a UART interface, and there's a good chance it'll just drop to a root shell, and at that point you're done, because then you can do everything. Now, and on that picture, there's also some JTAG that was also still left enabled. So JTAG is a debugging interface that gives you full control of the whole CPU. There's also a lot of devices out there where they just leave that hanging around and even label it for you. So they're really, really, really bad at security. But not all of them are. There's a few vendors who actually realize, yeah, a root shell is a bad idea. Let's prevent that. But as I said, they're using Linux, so and they don't really know what they're doing. For example, there's configuration files or stuff like that on a FAT32 SD card. I, for example, have one of those media players where you can just plug in an SD card. There's a configuration file on there which contains all kinds of blah stuff. It can read media stuff from there, and so on. And it has a file browser integrated, but that only allows me to read my SD card. But they're using Linux, and Linux supports ext2. So there's absolutely nothing that prevents me from reformatting my SD card and changing the file system to ext2. Now that doesn't gain me much, but I can create symlinks now. So symbolic links, I can just modify the file system to, for example, create a folder that's a symbolic link to the root of the whole file system. Then I plug the SD card into my device, go to the file browser, click on my symlink, and suddenly I can see their whole file system. So they just did not think about that, because they were like, yeah, it's FAT32, nothing can happen. But you can use this very, very easily to get an overview of everything that's on the device. And that's usually the first thing you want to be doing, because otherwise it's a complete black box. You cannot see anything. You just know that there's some kind of code running, whatever. And this usually gets you there. I mean, there's still the privilege separation of Linux you have to get around. But most of the time, they just run everything as root and don't care about permissions or anything like that. So this gives you everything you need. But let's go to the next class of bugs, which is a little bit more tricky to exploit. So those two things, you can just do them in a matter of a day or so, and maybe you've already owned your device then. But sometimes they're trying a little bit harder. So this was a gaming console that tried to verify if a bootloader was revoked, if I was still allowed to boot it. So on the x-axis, there's like the time, and there we have the RAM. I cannot access the RAM because it's a really, really high-speed bus. It's quite possibly encrypted, so I can't change anything there. But there's also the flash chip, which is soldered somewhere on the mainboard. I can go there, solder some wires to it, and actually modify it in place. I could even emulate it if I wanted to. And what a lot of people are doing is they first read the loader from flash to memory, because they want to decrypt it, verify it, and execute it in the end. So then they verify it, they figure out, hey, it's okay, I can run this. I'm still allowed to run this version of the bootloader, which, for example, but then later on we find a bug in that bootloader, and they want to revoke it. So at that time they also check for revocation and stuff like that. But then later on they read it again, because I don't know exactly why so many people are doing this, but maybe they want to save some memory in between the two times, I really don't know. And only at that point they actually jump to the code and run it. But as I mentioned, I can modify the flash memory if I want to. All I need to do is solder a few wires. And I completely suck at soldering, and even I usually manage to find the flash points, because they're usually exposed as test points or anything like that. What you do then is you wait until it loaded the thing for the first time. After that, you rewrite the flash memory with your own payload, with your own bootloader, with the still vulnerable version. And then it verifies the green version, which is still the original code. It still passes everything. But then the second time they read it, it actually contains your code. And it just jumps to your own code then. And well, those kind of bugs are called time of check to time of use, because there's a difference between the time, and you can modify something in between those two things. They're not only available if you, for example, have something on the flash memory. There's also this thing, which is from the Nintendo Wii. So what we did there was that we had some safe game exploit in the Legend of Zelda Twilight Princess game. And they did not like what we were doing there, so they fixed it. And they used this function here. Yeah, I have my mouse pointer. So they used this function here to check if a safe game that was going to be copied from the SD card to the internal memory contained our exploit. So, for example, on the left side, we have some safe game, so the safe game is essentially just a zip file with a little bit of encryption and signatures on there and stuff like that. So it contains multiple files. On the left side, they would find, hey, this Zelda tp.dat, it is evil, it contains some code. It would return and be like, oh yeah, no, I'm not going to run this code. But if you change the file a little bit differently, so if you added two files with the same name, which is really just modifying some header values, then they would run this checking function again. Now, if you take a look at the check function, if it figures out, hey, there's this Zelda tp.dat, it only checks the first file. So the first file there is nice, it contains no bug or nothing like that, so it will just continue. And then later, so this was the time of check, and then later comes the time of use. So then they go on, that function returned, hey, this file is totally fine and everything. Then later they copy the file to the NAND flash. And if you copy a file to their flash with the same name, it will just overwrite the older version. So you really just again bypass the time of check. You changed something in between. At the time of use, you actually get your evil file onto the flash. And there's lots and lots and lots of bugs like this everywhere. You really just have to look at some process the device is doing and think, okay, will it maybe try things twice? Will it maybe try to split the time between validating something and running something? Another example that I've seen is that when you install an update, it would first take the full update package, check the signature on it, make sure it's a legit package and that there's nothing modified there, and then copy it to the temporary directory as world writable. Then, after that, it would only move the files to the right place. Because the idea was we first want to have all the files on the temporary directory so that in case the system crashes or anything, we're not losing any. We don't destroy our file system. Because the move itself would be an atomic operation. But that time frame was enough. So after they put it in the temporary directory, you could just exchange the files with everything you wanted. They would still execute the move, and you again have full control of the system. So this is something to really look out for, because there's lots and lots of stuff like this happening. Another example, when you have configuration files that look like key value pairs. What they often do is, if it's running Linux, they're going to whitelist the keys because they don't want you to override system variables like the LD preloading path, the path in general. So they have a whitelist. And so they convert this to a small bash file with export key equals value, and then just source it during boot up. Again, the time of check happens when they whitelist the keys and convert it to a bash file. But yeah, the execution is separated because it will execute it later when it actually boots again. So you just do something like this. You give it a whitelisted key, set it to some kind of whatever value, and then it's running bash, so you can just add the semicolon, be like, hey, I want to run another command, and then it drops to a root shell, for example. Because obviously the config script has to be read as root because it's important or something. So if you see config files like that, or even if you see any kind of settings, just try to embed some kind of bash scripting in there, because they generally don't check for that, because they don't even think of that, I guess. Well, so I said, those are mostly kind of logic bugs that are happening on Linux. And now I'm going to more to the bugs that happen when they're using their own operating system and they designed their completely own system from scratch to hopefully be more secure. So what happens is that they think of memory like the top bar there. Just some kind of area, you can store bits and bytes there, whatever. It has a start and an end. But that is actually not true, because in hardware, you only have a limited lines of addresses going to your RAM. So you may have a 16, if you're talking about a small embedded device, you may have 16 address lines. So if you set the byte 17 to 1, it will just ignore it. So actually, memory usually looks like this. You get multiple mirror copies. And then they, for example, they might check to make sure that you're not copying. If, for example, the first RAM contains a section where there's secret keys or something like that, you have user mode code running. They might, for example, ensure that if you do a syscall, that your buffer is in a range that is secure. But if you just add a certain offset to get to the second mirror copy of the RAM, it will completely bypass that check, because they have obviously hard-coded the addresses to be from 100 to 200 or something, while the same thing will also live at 1100 to 1200. So if you see any kind of checks in system calls in custom devices, make sure that they just try adding large offsets to get to the next mirror copies. And another thing that they always do is, or the header verification, if you have an update or if you have some kind of package. What you should be doing is on the left there. So you have a fixed length header, and the very, 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 very first thing you should be doing is to validate the signature. Because after you validated that, you can be reasonably sure that there's no attacker tampering with your data. But what they usually do is that they want to have some kind of weird, variable length header and a signature at different kind of offsets, whatever. So what they do, they first copy the header and then already start passing data that is vulnerable, that you can just change with no consequences. And only after that, they go ahead and calculate the signature. So if you have update packages or any kind of thing you can give to the device, try changing all the header values. Just change single bits in there and check if there's different modes of failure. Because usually they even tell you, hey, the signature was invalid, or hey, there was an error with the header. They even have strings in there, like, yeah, signature verification failed, or I don't know, field blah, blah, blah is too large. And if the second thing happens, there's a really good chance that there's some integer overflow or some buffer overflow, whatever, in the process before they even go to the signature. Right, so here's an example how we managed to leak some keys using that. We had some kind of memory where they had the keys on the left part and had some public part to which we would write the package that we wanted to execute. And the first thing they did was to, for some reason, decrypt a signature. So a signature is not secret. It's just a really large number. You don't have to keep it secret. But still, they wanted to make sure that, I don't know, no one could see their signatures. That just shows that they have absolutely no idea how cryptography works. And obviously, the offset in the header to the signature wasn't validated enough. So what it would do, it would copy our payload from the public area to our secret area. And then we set the offset to the signature to a really, really huge value. And doing that, we could just make it decrypt anything we wanted in the public area. So I hope that makes sense. So you just set offsets to very high values and see if you can get it to decrypt something you did not want it to decrypt. All right. Only later we figured out that they also completely ignored the length of the header, so we had a nice text mesh. So we wouldn't even have needed to do anything crazy. It's just so really, usually those people are really, really, really stupid when it comes to security. We've been talking about custom OS. I've been talking about syscalls. So my first reaction to something like that is, hey, I'm going to write a fuzzer. I'm going to find some bugs in all those syscalls. Don't even do that. There's no need to write a fuzzer. Just open IDA and go syscall by syscall by syscall, and then you find stuff like that. For those of you who might not be familiar with privilege separation, if you're in user mode, you usually cannot write to certain regions of memory. And if you're in embedded devices in kernel mode, you can generally write everywhere. So when they have a syscall like that, they essentially allow you, that's a write anywhere primitive. So you can just go override the exception vectors. You can turn your own thread into root. You can, this is pretty much a really, really simple privilege escalation thing. And you really don't need to write fuzzers or anything. You just can go syscall by syscall and you'll find something like that. So that syscall was actually used to be something like write version somewhere. But instead you could just use this to knock out security checks in the kernel, because 0 happens to be no operation on the architecture where this happened. Yeah, now I'm going to come to the second part of the talk, where vendors really don't get how encryption works. And yeah. So if any one of you wants to write something with encryption, it's usually a good idea not to do it, because it is really, really, really easy to screw it up. There's 1,000 different things you can do to make your whole encryption completely useless. There's only a very few distinctive paths where it actually works. I mean, there's been recently this CryptoCat thing where they were using public keys with a very, very short length. So that was a very obvious bug, but there's a lot of them who are not as obvious. For example, there's stream ciphers. They're a really nice invention because they're usually fast. You can skip ahead to any part and just decrypt anything you want. How they usually work is that you have a secret key and a nonce. You combine that together, and then you get just something like a cipher stream, which is essentially just lots and lots and lots and lots of random numbers. Then you take the plain text. In this case, only SIG. I wanted to SIG in, but it just didn't fit on the slide. And you take that and combine them with an operation that is called exclusive OR. So exclusive OR means they look at every single bit individually, and if exactly one of those 2 bits is 1, the result is 1, and otherwise it is 0. So they're using this function because it makes decryption and encryption work exactly the same. You just fire up your stream cipher again, generate your random stream, and now you either apply it to the plain text, you get ciphertext, or you apply it to the ciphertext and you get plain text again. And that thing called nonce is called number used once for a reason. So I guess you already can figure where I'm going here. I've seen this so many times that they just reuse this number. And what happens then is that you encrypt two things with the same cipher stream. So then you take those 2 encrypted things, XOR them together again, and you're usually going to see plain text. And for example, I use this to extract some secret operating system files from a flash device. So again, at the top you have the flash. I can read that out. I can change the top thing at will. Then we have the secret CTR mode cipher stream. I don't know that one because it was generated somewhere in hardware. And at the bottom you have the unencrypted FS. This is how you see it from user mode, for example. And so what I did, obviously they were reusing the stream for every single iteration. So they had the flash, and they just always applied the same XOR stream, whatever was written there. So now I just created a really huge file that just consisted of zeros. And as I just mentioned, if you XOR something, it becomes 0 if both are 0, and 1 if one of those things is 1. So if you take a stream of zeros, just create a huge file, and then write it to the flash, it will just write out the cipher stream for you. Then you just revert the flash back as you have hardware, but you keep a copy of the cipher stream. Now you go to the system update feature. It will go ahead and put a system update somewhere on the flash for you, which will sadly be encrypted, but that's not a problem at this point anymore because you just extracted the cipher stream. So now you can just go ahead and decrypt their system updates. And all that because they were using counter mode keys. This is not only happening on flash devices. I've also seen this on updates. So this was how I initially got into some device because I had just two executable files, extract them together, and suddenly saw strings and everything there, and by pure luck, I also found some keys in there. So there's also something you can try. Just take update files, take every files they have, try to extract them together and see if you can see something like strings. And if you see something like strings, you can be very sure that they screwed up. But some of them aren't using counter modes. They're using so-called unauthenticated modes, which really just means you take, so this is from Wikipedia, for example. It doesn't really matter if you exactly understand what's happening here. In general, it just means you convert a cipher that works on 16 bytes, like AES, for example, to a cipher that works on as many bytes as you want to. The problem with that cipher is that if you change at any point in your plaintext, flip a single bit, in the ciphertext, all the following bits will be completely different. So that is why when they use those modes for flash or hard drive encryption, they have to split the whole thing into sectors, which are usually like 8 kilobytes or something like that. And we're just going to do the same trick again. There's some operating system file on our hard disk. We cannot read that because that's the unencrypted FS layer again. So all we can see is the encrypted data that gets stored on the physical flash. And their operating system is preventing us from accessing that file there. So what we do is we create a user file again, which will be converted to something boring. Now the problem is that I mentioned that they're using unauthenticated encryption. That means I can take the ciphertext from my encrypted operating system file, move it over to where my user file lived now. And what happens then is that when I go ahead in user mode, start reading it again, my boring old user file turns into the operating system file. And by using this, you can essentially extract the whole hard disk they have. Because you just take all the blocks, move it to the block that you own, read it, reboot, repeat the same, and so on, and so on, and so on. As I mentioned, it's really easy to screw up crypto. Don't invent your own crypto system. Use well-known algorithms. For example, in those cases, they should have used something that's called XTS mode, which was just invented to prevent those kind of problems. And then there's also like the really bad examples. There's, for example, the Nintendo edition of RSA. So what they did was they took the RSA signature together with their public key and generated the above hash, which, there's something missing on the left. So the top thing says RSA, and the bottom thing says calculated. So calculated is my evil file that I used. It hashes to that thing. It expects the top hash. Now, if they had been using memory compare, it would fail at the second byte, because the second bytes are different. But some engineer apparently wanted to optimize the whole process a bit and decided to use a string copy function instead. Now, string copy functions stop if they see a 0 byte. And so if you just brute force the hashes well enough so that the first byte happens to be a 0 byte, you can create signatures that seem to be completely legitimate to the console. So even if they do implement the right cryptographic primitives, make sure to actually go through the code. Because when I see something RSA, my first reaction is, oh yeah, that's RSA, whatever, it's going to work. Go through the code, read every single line, because otherwise you'll miss stuff like that. There was a different screw up where they were using another algorithm. I guess you know what I'm talking about. So they were using elliptic curve DSA, and the important thing there is, for every signature, you create a different random number. Now, if your random number generator is a little bit broken, like the one they used, you can just go and leak private keys. And this didn't only happen to one company. There's at least 2 cases that I'm aware of where they forgot to use a real good random number generator. So the conclusion here is never, ever assume that they get their crypto right. A good assumption is when you have some device that's trying to use cryptography that it's completely wrong and broken, because there's a good chance that it is. And now comes the last really interesting bug. We're going to brute force some AES keys. So generally, AES keys have a complexity of like 128-bit. And before you're going to be able to brute force something like that, the universe will probably die from an entropy death or something like that. So generally, you can't brute force AES keys. But some vendors are clever. They hide AES keys in hardware. So they have a bootloader that writes the key to a write once register. So write once really means you can write to it, but you can never read from it again. After that, all is happening in hardware. So the hardware gets initialized, it uses a scrambling function, or maybe it doesn't even use a scrambling function, it just hides the key from you. You can still decrypt and encrypt things by poking some magic value somewhere, but you cannot read the key. But again, you can still encrypt things. And you can maybe even partially overwrite the key. Because registers, there's no 128-bit registers. Usually they're more like 32-bit or 8-bit. So it may even look like this. And if you get the system in this state, where you can encrypt and decrypt things, at first you leave everything as it is. Then you take some known plain text, encrypt it, and you get some kind of ciphertext. Now you start overwriting the very first byte of the key with something like this. You cannot read anything, but you just change the first byte of the key. You encrypt your same plain text. Take a look at the ciphertext. Does it look the same? Does it change? OK, it changed. So let's overwrite the first byte with a 0, 1 then. Yeah, still not the same thing. Let's try 0, 2 or 0, 3, and so on and so on. So you just brute force the first byte of your AES key. And once you reach, whoops, that was one thing too far. If only I knew how to use Keynote right now. Right, so if you then, at that point where you reach the correct first byte, and you encrypt your known plain text again, you get some ciphertext that matches the ciphertext you had at the beginning. And then you know the first byte of the key has to be AA. And then you go on and repeat the process 16 times, yes, you get the whole key. So if you ever run into some kind of obfuscated keys, try overwriting it byte by byte by byte by byte. What should be happening is when you overwrite the first byte, it clears the whole key, but most of the time they just forgot to do that. And you can pretty much use the same attack against message authentication codes. So for those of you who don't know how they work, it's really you take a hash function, you take a key, and you take some kind of binary. They're somehow all combined together and result in some string that authenticates your binary. The idea is that you don't want to use some kind of fancy asymmetric cryptography things because they're hard to implement or something. You want something simple. All you want to do is you want to hash the binary and get some authenticated string out of it. And a lot of people use this for the first stage or second stage bootloader authentication. The Xbox used this. The Xbox 360 actually used this for a later stage as well. And you cannot calculate that kind of MAC. So you go modify the file. The file is loaded by your device. The device calculates the correct message authentication code, and then it goes ahead and compares it with the authentication code you provided. Usually, they use memory compare function for this. How those functions work is they go ahead and compare the first byte. Is it the same? OK, no, it isn't, and they fail. If the first byte is correct, they go ahead to the second byte, compare the second byte. Are they equal? And if they aren't, it's going to fail again. Again, you use the same strategy, but this time you measure the timing. Because if the memory compare function actually manages to reach the second byte, it will take just a little bit longer before it's going to fail. Because it verified the first byte. If it's wrong, it's immediately going to fail. If it manages to go ahead to the second byte, it takes a few more clock cycles until it gets there. So really, you just reboot your device over and over and over again You continue modifying the first byte until at some point you notice it just took just a fraction of a second longer to boot. And at that point, you know that you've just found the first byte of the message authentication code. You repeat this again until you get the whole full thing. So what's the conclusion of all of this? Most vendors who try to do security completely suck. I mean, those bugs, they were mostly very easy. You did not need to bypass any kind of fancy security features like deep execution prevention, address space layout randomization, any of that crazy stuff. You didn't even have to touch it. So what I'm trying to tell you is, if you try to break an embedded device, try not to even think about the crazy stuff. Just try to think about very logic bugs. Try to use your knowledge of Linux, how Linux works, and assume that the vendor does not know how it works. Just try to find some way to make those devices do something differently. All right, and now I still have some time for questions. Do we have some kind of microphone? Oh, yes, of course, that works as well.
Yeah, what was the first starting device? What was the first hardware that you were doing?
All right, so the question was what my first starting device was. What was the first device that I tried to break into? And for me, it was an old DVD drive. As I already mentioned, I worked on the Wii a little bit, so I wanted to take a look at their discs. Their discs are somewhat different from normal DVDs. They don't just work in your DVD drive. So I was trying to hack my DVD drive to accept different disks. The DVD drive is a really simple thing. They have absolutely no security. You can really just go ahead and take a look at the firmware, modify it, understand it. And I think I worked for around 2 years on that. I didn't really get anywhere, but I really learned a lot during that time. So again, just start with something really simple. Any more questions?
So if a device doesn't have an obvious serial port or a JTAG connector and you know it runs Linux, are there any other debug interfaces?
So the question was, if you have some kind of device which is running Linux and you don't find any obvious serial ports or obvious debug faces on the main board, if there's any other things you can do. So what I would try next is if it has a network connection to port scan it and figure out what software is running. Because there's a good chance that they're using software that's at least 3 years old. Because they generally, I don't know why, but they generally take some old version and never ever update it again. Then you just Google for some software version vulnerability exploit and use the first result and run it and usually get a shell as well. Or you can also try to telnet to it and try empty root passwords or the name of the vendor as a root password. That would be my very next attempt. Yes?
What kind of tool do you use for the timing attacks on event copy?
Okay, so yeah, that's so the question was, what kind of tools do you use for timing attacks on the memory compare in the end? So that really depends on well, actually, it doesn't depend. I'm using FPGAs, which are kind of, yes, they're really flexible logic. You can build flexible hardware logic in them. And they're really accurate and really fast. But you may not need to use them because sometimes if you can manage to slow your device down, you can, for example, take a look and find the clock, replace it with a clock that's like 1/10 of the original frequency. Some random microcontroller like your Arduino or a Raspberry Pi or something like that may already be enough to get an accurate enough timing measurement. And another thing, if you see a lot of jittering, so if you just reboot it and it's always different by a few milliseconds or something, just try with the same byte, try it like 20, 30, 40 times and take the average out of it. Because that usually helps to actually see the difference, because the difference when it goes to the second byte will be like a lot larger. Yes?
Do you know of any device, any company who's actually doing everything right? Do you have some examples? Or do you think?
Okay. Okay, so the question was if I know about any company or any vendor that does everything right, or if there's no such thing like that. So in general, I don't think you can do everything right. You can only try to be really, really good, but in the end, someone will break in your device. It's going to happen anyway, so you might as well not bother and allow us to run Linux in the first place. That would be doing it right, in my opinion. And there's two examples that I like to cite. The first one is the Xbox 360. They had a really, really good security system. It was really well thought out. The problem is that they did not take hardware attacks into account. So from the software side, they really did everything right. You can watch the talks by Felix Domke and Michael Steil about the security system. They're on the CCC website. It's usually during the Chaos Communication Congress. And so software-wise, they did everything right. Well, the hardware, yeah, well, they failed there completely. The other thing is that Sony's PlayStation 3 was actually really good for 4 years because it was running Linux and no one was breaking into it. And that would be, in my opinion, really doing it right. Just allow us to run Linux, maybe disable the GPU, maybe clock down the CPU or something. If you just allow people to run some code on it, you greatly decrease the chance of anyone hacking it. And I'm looking forward to the new Xbox because supposedly they've learned from their mistakes there. So that may be a candidate for doing everything right. Yes?
I'm not a programmer, but I just want to say that no matter how secure your encryption protocol is, if you're like the system admin or something, and there's ways for long distance electromagnetic reading of your inner thought that so your password and your passphrase, they are very vulnerable.
Right.
Even if your system is very well encrypted. And I have lots of information if you're more interested in that kind of security.
All right, so he just mentioned that even if you have the perfect security and everything else, there's still electromagnetic emissions from your laptop, and you can pick them up.
And also from your head.
Right, of course, you're right. Yeah. Oh, from your head.
Yes.
You mean like from your... Okay, that sounds crazy. So he's talking about something like reading thoughts.
So there's a patent in 1974 by Robert Allen. He was able, with a matter of meters at that point, where he could illuminate the brain in his words with sending signals between 100 megahertz and 40 gigahertz in the spectrum. And by reading the return patterns, he could get a full electrical reading of the brain. And you can combine that with the analysis that has been done in this time frame. Then you can and also consider satellites and ionospheric heaters, which are really just over the horizon mind-reading radar. This is how intelligence agencies work, and I think people should be aware of this if you're interested in security.
All right. All right. So he's essentially telling you that we're all screwed anyway.
There are ways that people are trying to defend themselves on that list. So if you're interested, you can talk.
Yes. All right, any more questions? Because I don't think we have much time left. Or is there even a talk after mine? Yeah, but it doesn't look like there are any more questions anyway. Oh yes, there's actually one more question. Oh, I'll just repeat the question.
When you say, okay, once somebody will break into your device,
Yes.
do you have good example of attention depth so that when a single device breaks, then it limits damage to that single device? I assume most vendors will be okay with you breaking into their device, as long as not the whole wall can do it.
All right, so the question was if I know of any examples where the vendor prevents that if I break into one device, I don't get enough information to break into any device easily. So that thing is actually called a hero attack. So hero attack is you just need to take one device individually, break it under a really huge effort, and after that you can take all other devices down very easily. And I haven't seen anything like that yet. So I know that in HDCP there's some feature that was originally intended to be able to blacklist individual drives. So the idea was if one drive key leaks, they can figure out which key that was and then blacklist the device eventually, but that was implemented completely wrong, I guess. But so they tried to do that, but I haven't seen anything like that actually working so far. Say again, please. Yeah, exactly, the Blu-ray encryption. Oh, yeah, sorry, I mean ACS, sorry, not HTTP. Yes. So they tried it there, but I don't think it worked out. They haven't seen anything like that actually working so far. And there's one more question over there. Yes. Say that again, please. All right. So the question was what kind of disclosure mechanisms I prefer. It's a bit of background. There's usually, so I know about full disclosure and responsible disclosure, where full disclosure means you just put everything out there and wait for a reaction, and responsible disclosure means that you actually contact the company and try to work out something. And I actually prefer the responsible disclosure thing, because that usually results in everyone being happy unless the company still threatens to sue you afterwards. I guess there's time for one more question, maybe. All right, guess there aren't any more questions then. So thanks for your attention.